We are Team MSG presenting our solution for the wind energy production forecast. Here's the table of content that we'll be presenting in the next few slides. Wind energy is an important source of energy for France. However, the fluctuation of wind speed and its direction would impact the energy forecast. Taking up the role as the energy trader, our objective is to maximize our client's profit, employing deep learning to forecast a window of T plus 18-hour energy across 8 farms in the Ile-de-France region. Here's the data set for wind energy. Wind energy comes in the short bursts of high production. We aim to produce a neural network that can anticipate and predict such short bursts to ultimately produce an accurate forecast such that our client will be able to reap as much profit without incurring any losses or penalties due to misprediction. This pattern of historical wind speed forecast is seen across 6 farms in the Ile-de-France region. The pattern observed is short bursts of high wind speed, which in turn produces short bursts of high energy production. This is the historical wind direction forecast from the 6 wind farms. As observed, there isn't much of a visible pattern to discern from. We have excluded 2 smallest wind farms from the dataset to reduce the unnecessary iteration for weak reduction, due to having a low production of less than 1%. Both wind speed and direction were then averaged respectively from 2 models that are provided into a single source. Since they are highly correlated and forecast the same data, we have chosen to normalize both energy and wind speed data to unify the scale for better result. We also applied the sine and cosine function respectively to normalize the wind direction. The model building process itself proceeds by trial and error, making educated guesses on possible features. The model adapts to the constant changes based on improvement observation from loss graph, lag correlation, and more. These are the window sizes that we have considered. Using window sizes beyond T plus 18 for wind forecast proved unfruitful. Using a larger window sizes than the above also gave a poor result. These are the plausible features that we consider as input into our network. This is our neural network. The input X will come from the above into the top layer of perceptrons. Each perceptron will output a value and pass it on to the next layer, which only contains 2/3 of the number of perceptrons in the previous layer. The network culminates with a linear combiner, which ultimately gives rise to the prediction. We examined with many different features and ended up using different window, skewness, and median. These features achieve the best result among all other configurations that we have tested. There are approximately 481 neurons in our neural network, 200 in the top layer and fewer in the subsequent layer. The dropout probability chosen was 0.3 to reduce the noise introduced by the data. The solver we have chosen is Adam, while the saturator used is ReLU. The subsequent slide depicts our losses, scatter plots, lag, and prediction graph for our result respectively. Our test losses beats persistent. This is our scatter plot. You can see that the point leans downwards slightly, meaning our model tends to under-predict. Our model has no positive lag, which is a good thing, even though there's still room for improvement. Here's the prediction for test and train. As seen from this graph as well, our model does not have positive lag. It is able to follow the trends in energy production quite well, although it will be a hit and miss situation when it comes to how much the energy production will spike. Due to the features and respective window we have chosen, our model relies heavily on the availability and reliability of wind forecasts provided. The performance of our model could be affected if the wind forecast data provided is not accurate. This is a risk of our model, since forecast data might not always be available or accurate. When we did not fed forecast data into our model during training phase, the model build did not give satisfactory result. Because our model relies heavily on pattern of change to predict the next change in energy production, it can produce observed results such as negative energy production or absurdly high forecast. The historical energy data shows to the human eye that the energy is kept within certain limit. This is something our model couldn't appreciate and thus requires the output to be checked externally. Thank you very much, and we are from Team MSG.